In this video, I'm going to use Wolfram-Cloud Mathematica to play with Bertrand's Paradox. And this is based on a video, a number file video, that address. So there it is. And so you have this circle, and you are going to make chords of the circle. And then you have this, you can imagine a inscribed equilateral triangle, and if this circle is a uniform circle, has a radius of 1, then the side of this triangle is the square root of 3. So that's going to pop up. So we're going to make chords in the circle and ask if those chords have are larger than the side of this triangle or not, and then it'll all be down to this sort of question of like what's the proper distribution of chords to pick from, and you want to know sort of what the fraction is that have greater than or less than this value, and it sort of depends on the distribution of chords that you're pulling from. Okay, so, and he had 3 versions. I'm going to have 4, so I'm trying to duplicate my first 3, his 3, and then offer yet another one. So the first sort of definition of chord, to pick a random chord, is that the chord connects 2 points along the circle. So pick 2 points along the circle. I can, since it's a unit circle, I can pick just angles between 0 and 2 pi, pick 2 of them, and then have those correspond to x and y points, find the distance between those points, ask if it's greater than the square root of 3. So here's my little simulation. I'm going to have 1,000 samples. This is going to be my count of times when I am greater. I'm going to, so here's my Mathematica for loop. For is a method. It's got 4 arguments: the initialization, the condition to stay in, the incrementation, and then what I want to do inside. And I'm going to pick, so I'm going to have a uniform distribution from 0 to 2 pi. I'm going to pick a random number from that. So uniform distribution, random variate, pick 2 angles, angle 1, angle 2. And then the x down below, I start using the notation x1, x2, y, x1, y1, x2, y2, but here I did not. But the x is the cosine. And so this is sort of x1 and x2, and this is y1 and y2, and I took the difference of the x's and squared and the difference of the y's and squared, and then took the square root, so that should be the distance. And then if it was bigger than the square root of 3, I incremented my counter, and then I got my counter divided by number of samples. I got the numerical value. I printed it out. And the idea here in this version is you pick 2 points. You can sort of, without loss of generality, imagine that your first point was one of the vertices of the equilateral triangle, and then the other point is somewhere on the circle, and the equilateral triangle breaks up the circumference into thirds, and if the other point is on this bottom third, sort of farthest away from this point, then that distance will be larger than a side and otherwise will not. So you're expecting from this definition, this way of constructing your chords, you're expecting an answer of 1/3, and there the simulation is getting close to 1/3. And then this is just mostly a repeat, except I'm going to draw the chords. And so I have getting angle 1, angle 2, calculating this distance, testing the conditions greater than square root of 3. But I'm going to make a collection of chords that are smaller and chords that are bigger. So this is a list, an empty list to collect them. And here I'm creating a line from, so if my if function or my if method has a condition and what to do if it's true and what to do if it's false. And if I have more than one thing I want to do, like if it's true, I want to increment a counter and add a line, then I separate those things by semicolons. So there are 3 things in an if separated by commas, but one of those things may involve multiple steps, and those things are separated by semicolons. Okay. So I'm adding a line to bigger if the condition is true, and I'm adding that line to smaller if it's false. And then I'm also calculating again. And there it is, close to a third again, the different value because it's random. But now I'm going to show the bigger in red and the smaller in blue, and also draw a circle of radius 1. And then I'm also going to draw a circle with a radius of half, and you'll see why in a second. Okay. So we see these, the reds and the blues. Okay, so the bigger ones were the red. So the ones then seem to go through the middle are the bigger ones. Okay, so this comes up with, and then I drew this white dashed thing here that I think you can see, is that a circle with a radius of a half. So another way of thinking about this is to say that, like, if my midpoint is in this circle, then it will be larger and otherwise not. And this, so I can sort of draw a point, imagine this is version 2, but this is how version 1, in some sense, this picture of version 1 leads us to version 2. That we can see this inner circle with the radius that's half of the other one playing a role. And so that's what the sort of version 2 does, is says, I have this circle with half the radius. And if I were just sort of going by the area of these two, this inner circle having a radius of a half, and then if I'm working with areas and that half gets squared to get me the area, then that suggests a quarter. So shouldn't the answer then somehow be a quarter? Well, it depends how you do it. And so what they, in version 2, they say, take a random point in the circle and then make that point the midpoint of a chord, and then find out if that chord is larger than or smaller than the side of the equilateral triangle. And then just by playing around looking at this area, then you expect, when you pick a random point and construct a chord from it, but you're constructing the chords that you construct that were from the inner circle will be large enough, and the ones in the outer circle will be small enough, so you're expecting an answer of a quarter. Okay, so let's play the game that way. So first, I just want to pick random points around a circle. So I'm not doing any chords. I am here. I chose, I think, 10,000 just to have a lot of points. I'm just doing points. I'm not going to do chords. I am looping through. I am picking a random angle, sort of as above. But the other thing I'm picking is a random number between 0 and 1, but I'm taking its square root. So when you want uniform, you don't want to pick just when you're picking random points distributed through the square, through the circle, you don't want the radius to have a uniform distribution, but to have a square root distribution. So you get the uniform distribution, and then you take the square root of it. And then I'm just adding points. This is like a Mathematica thing. There are circles and lines and points, and these are graphical. So then I can use graphics and show it. And so I make this collection of points, and at least that looks pretty uniform to me. And so that suggests that this sort of square root thing is the right thing to do to get the points uniform. And now I want to construct from a point a chord. And the idea was that the point should be the midpoint of the chord. That was just part of the construction. Whether that's the right thing to do, that's all part of the paradox. Is it the right thing to do? All right. So in general, I'm picking a radius and an angle. I'm going to hold off on the angle, and I'm just imagining then I have the radius, which was some number between 0 and 1. Um, and then I want to make a chord where it's the midway. So I'm ignoring the angle I chose for the moment, and imagine that R is along the horizontal axis. Then I want to, then the chord, which it is the midpoint, is this vertical, and I want to know this angle so I can find these points. And if this is R and it's a unit circle, then the angle is the arc cosine of R. Okay. And then so this point, then if I know that angle, then I can figure out the x and the y of this point. Okay, so you're going to see this angle, you're going to see these arc cosines float. And then I'm going to bring in, and then I'm going to take those x and y points of the endpoints of my chord, and then I'm going to take the angle that I chose and perform a rotation. So let's see that popping up in what we have here. So first I'm just going to do 10 and draw them to see, like, am I getting what I think I wanted to get? Okay, so I'm getting my random angles. I'm getting my random radius. Again, I've got that square root, which seemed to make sense above and give me the uniform distribution of points. I had my x's were, before I rotate, my x's are my radius, and my y's were sine of the arc cosine of my radius. And I, down below, I show that simplifies, and I didn't simplify it. So probably making Mathematica work harder than I need to. But where was that picture again? If this was R, the X the x position of this point was r, and then it's a uniform unit circle. So the radius was 1, but then the sine of the angle, and it's the sine of the arc cosine of r. So that's this weird sine of r cosine of my radius. So that is sort of my original y, and this was my original x. And then I performed a normal rotation through the angle, and that was you multiply the x by cosine and the y by minus sine to get the new x when you rotate, and to get the new y, you multiply the x by sine and the y by cosine. So that is sort of a rotational transformation. And I did it for the x and the y. And the difference between the x and the y is the sine of the y's. Because once I was going up and once I was going down. Okay. So let's draw that. Okay. So I am picking, and I'm only doing 10 right now. I am picking random points within the circle, and then I am constructing a chord at which that point is the center. And that looks good to me. I think those points look like they're the centers. And so then I ramped it up to 1,000 samples and had 2 sets of chords, because I'm going to have inner chords and outer chords. And then I'm going to run it all up. And here we're getting values close to a quarter, because we're constructing chords. Once we have the point, we're just going through all the machinery to make a chord, so I can draw it, to make a chord that has a midpoint, has that point as its midpoint. But we know then if we're in the inner circle, it's large, and the outer circle, it's not big enough, and that the area of the inner circle was a quarter of the whole area. So expecting an answer of a quarter, and there it is. And then let's do the picture. And this is our picture, but we see, while this seemed to be the right distribution of, now this is like 10 times as many points, because I did 10,000 for just these points. I never did run that for you. But pretty much just reproduces what I sort of had, except, slightly different because it's random. But while that selection of points seems to be, a good criteria for selecting points, it's questionable whether it's a good criteria for choosing chords, because there seems to be just this emptiness in the middle. Okay, so now here I'm just sort of showing that above I had that sine of arc cosine of x, and that could have been simplified. I was trying to show where it came from, and then I was just being lazy and not doing the substitution myself. Okay. So anyway, now we see this sort of emptiness of chords, not dearth of chords in the middle. So it's a paradox. So some people will just say, you need to define it better. Just be more careful. Now here the question is the original good or not? Doesn't seem to have as much of a dearth of chords. It may seem to be a little thicker on the edges, but this really seems to be, sort of hollow in the middle. Um, and so the third version um, that they talk about in the number file video was to pick a radial direction at random. And so that's an angle. And then, so you're, say, in the center and you pick a random direction. And then you imagine that you're somewhere along that radius. And so, sorry, you choose a random direction, and then you move that random direction sort of a uh, along a direction, and then along a radial direction, and then you pick one direction and you move it sort of more or less at right angles perpendicular to that. So you would pick a sort of a random direction and then you would move it, and then you see sort of what radius do you need for it to be big enough. And it is, if you're sort of at half the radius, it's in. So it's and then they're expecting answer of half. So it's sort of very much like the previous one, except we're choosing our points. If I were just using this to choose points, you see it's sort of far too dense in the middle. Let's try to say what I'm doing again. I am picking an angle that sort of gives me a direction of my chord, and then I'm sort of picking a a position along the radius for this chord, and we're saying we're going to do that uniform, and we don't have the square root here. So if we're just using this to pick points, we got a lot more points in the middle. That's sort of why we took the square root before, to get rid of that. But in this approach where you pick the sort of radial direction, and then you pick like a position for that radial direction, the suggestion was that that is uniform, to take it as uniform now. And now this was just points, no chords just yet, just the points. But we see that in terms of points, it's denser. It's the same game as above. I did the same sine of arc cosine. It's all the same above. And all I really did was take out the square root. And now we're getting something close to a half. Okay. So that was the third approach mentioned in the video, to pick a random, I'm picking a random R and an angle and a radius again, but I'm picking the radius, I'm picking uniform radius between 0 and 1 without any square root. So if I'm thinking of it as points, the points aren't evenly distributed, but maybe the chords are. So if I make my graphic, this seems to have filled in the chords. So in version 2, it seemed to be empty. There seemed to be a dearth of chords. This one seems to be more filled in. Okay, seems to have more chords all the way around. Okay. I made a version 4, and glutton that I am. And I'm going to return sort of uh, in version 2. I picked a point and I made the chord. I did constructed my chord from that point by making it the midpoint of the chord. What I decided to do in my version 4 was pick a point and then pick another angle and have that second angle. So I'm picking a radius and an angle to pick a point, and then I'm picking another angle, which will be the slope of the chord. Okay. So I have points and I have chords. I'm going to do a small number in the beginning, just 10, to sort of, so you can see what it is I'm grabbing, and then I'll do a lot of them. Okay, so my angle and my radius, I'm back to the square root. So that is, I'm going to pick a point in my circle, picking a point in my circle. I'm going to have another angle, and that is going to be chosen at random, and then that's going to be the slope of my chord. So before, when I chose a point, I made it the midpoint, and that fixed the slope. But now I am going to pick the slope by choosing another random variable. Okay. So now I have I sort of did this again. I chose just to move R along the horizontal, but now it's not going to be some vertical, but I'm going to choose my second angle is going to be this slope, the slope of my chord. And so then I have some sort of quadratic formula that I solve to get two solutions, the two endpoints of the chord. And then like I did before, rotate my angle theta. So I hold off. Uh, I have my angle and my radius to pick a point somewhere in the circle. I have the square root, so that gives me the more uniform distribution of points within the circle. This angle 2 is going to be the slope of the chord. And then I'm doing this root 1 and root 2. This is a sort of a quadratic formula to find the to find those two chords, to find the endpoints of the chord that are on the circle. Okay. So, and then I do the rotation. So first I'm just my points is easy. It's my radius times cosine of my angle. I am finding my radius was the original x, and then here was working with a root and adding. There was a positive root and a negative root, root 1 and root 2 of a quadratic formula, and that gave me the root 1 gave me the one endpoint of my chord. The root 2 gave me the other endpoint of my chord, and then I used the original angle to rotate it. And then I added the chords. Okay. So here's what I have now. So I have points with chords, and they're no longer the midpoints. So I don't have that restriction anymore. I mean, this one looks like to be towards the middle, but this one's way sort of near the end. So pick a point, pick a direction, and then just find the endpoints. Okay. And so now I'm just doing that with a bigger sample, and I'm going to compare to my square root of 3. Down here somewhere, I have all this math of finding the x1 and the y1, the endpoints of the chord, finding the distance between the x and the y squared, and take the square root, and find out if it's bigger than the square root of 3, and make these different size chords. Okay, so run all this. And here I keep getting numbers around 0.6, not so. And then I draw it. And this one, if anything, seems to be denser in the middle. So maybe, I don't know, maybe this technique is sort of overdone it. So now they talk about in the video, and especially in like, there's a follow-up video, um, that, there may be some additional symmetry and some additional symmetry reason to prefer version 3, the third method, that um, that this sort of, it seems maybe this one has the most uniform density of chords, and so it might in some way be a preferred answer. But the whole thing just says depends on how I get different answers depending on how I pick my chords, define my chords, what distribution then I pull my chords from. So that's the paradox. I'm not going to tell you the answer to the paradox. I'm not sure I know, but I just wanted to play around with Mathematica and reproduce some of those results. Thanks for your attention.